Since I've used the rectangular maze as an example, I think it's time I show you some actual code running to demonstrate how these rectangular mazes would look. There's an interesting twist on this problem. You can use depth-first search to search a rectangular maze and find a solution from start to finish. But you might ask yourself, how do they create these mazes in the first place? If you ever had to do one by hand, as I've tried to do for my kindergartner, it's really annoying. And before you know it, you end up with a maze that doesn't look at all like a maze. And the harder you work, the less it looks like a maze. It turns out you can actually use depth-first search to create the maze in the first place. Let me explain. So you can start with a graph which is a fully represented graph. By that I mean every neighbor that exists. So if I start here with a maze, which is a 10 by 10 maze, and I start with this idea that there's a starting place up here and there's an ending place down here. Initially, there were walls everywhere, so that clearly I can't make any progress. But look at this maze through the eyes of a depth-first traversal and ask yourself, if I start here, can I visit one of my neighbors? Do I have any neighbors? Well, actually, I've got 3. One to the left, one below, one to the right. Have any of them been visited yet? No. Okay. Break through that wall, pick one at random, and go in that direction. So you can actually use depth-first search with a random twist to start with a maze that's fully built with all these walls and break through the walls when you're randomly choosing a direction to go. And if you follow this approach, you actually end up with a maze that looks like this, which quite honestly is probably better than anything I could have drawn by hand. I'm going to demonstrate how to do this in code using tkinter again to demonstrate a nice graphical front for this. The code I'm about to show you is going to be a Python implementation for generating a rectangular maze, using depth-first traversal for that possibility, not just to search, but to actually construct the maze. Along the way, you'll see some tkinter code, and again, I don't have full time to explain all of its details, but I believe after seeing the code and further exploration on your own, you'll figure it out. I'm going to create a class called maze that will store information about the maze that I'm interested in. Specifically, what's its height, width, and what is the number of pixels you want in the squares. Because after all, I want to represent this visually. And once I store that information, I'm going to construct the maze. Now, the thing that's interesting about the maze, as I just mentioned, I want to start with a fully rectangular grid where every wall exists. And I want to have a designated start and a designated end. And I want to use depth-first traversal to knock down walls and thereby create a maze. To make this work, I've got to store some information. And so let's start with that here, the construct. I need to keep track of the walls. And so I need to have horizontal and vertical walls. The east walls are the walls that are vertical on the east side of a room, and the south walls are the walls that are horizontal on the south side of the room. With that in mind, I can determine all the status of each individual wall in the maze. I need to keep track of the color of each of those squares, and a square is going to be identified uniquely by a row and a column. A tuple will uniquely identify that. The colors associated with each square will initially be white, because that's my initial setup. I also want to keep track of all the neighbors that might be present. And every neighbor in a cell, in a maze, has potentially 4 neighbors. Horizontally there are 2, and vertically there are 2. If you're at the corner, you only have 2, and if you're at an edge, you might only have 3. I'm going to construct the maze so that every wall is present, all the east walls, all the west walls. And I'm going to do a little bit of work to record all the neighbors for every cell. And for me, a cell is going to be the tuple, or designated row in a column. Once I have all that information, I designate a home square, which is the middle of the top row. 0 is the row, and how many columns I have? Well, halfway through, that's where my starting is. And then I want to do a depth-first search from that point on to the rest of the maze. And then I'm going to designate that there is no south wall for the last row, the center. So this is the maze where I'm going to start at the middle square on the top row, and I want to end at the middle square on the bottom row. And along the way, I'm going to use depth-first visit to do the work for me. I will show you the depth first visit in recursive form, and then you'll realize it's not going to work for very large mazes, and I'll have to implement a different version for non-recursion, but it's easier to talk about the recursive one first. You've seen the depth first recursive before. Here it is. To do depth first traversal over a graph, you have to color it first and say this vertex is now gray, and then find one of your neighbors that's white, and then go in that direction. Here, what's really interesting is I'm using the exact same approach to construct the maze. The first thing I do is I mark that square as gray, which means I've visited that square. I then look at my neighbors, and I choose a random neighbor that I might have. If that neighbor is white, then that means I haven't visited yet, and I clear the wall between us and then traverse in that direction. So this is a really interesting twist on what depth first search does. The structure is identical, and if you think about it, if you're going to use depth first search as your algorithm for solving a maze, then in this virtual arms race, I'm going to use depth first search to create the maze in the first place, to make it as challenging as I can for you, as an adversary would. And this depth first search visit is recursive. It marks the color of that square as being gray, finds a random neighbor that's white, and then goes in that direction. If it turns out that that neighbor has already been visited, then I won't recurse in that direction, and I will remove it from the list. This guarantees that I will traverse all the cells exactly once, and then when I'm done, I've completely visited all the cells in the maze. The only parts that's left are some really interesting graphical stuff where, for example, here, this is how I clear a wall between two cells. If the two cells have the same column coordinate, that means that they're neighboring one over the other. So I can remove the south wall, which is that horizontal one that separates them. If, however, the two cells have their row coordinate in common, it means that they're neighboring, and this is an east wall that I need to remove. So with this one simple function, I can blast away any walls that exist. And then the last thing that's needed is a function called view that goes through and creates all the lines that I need to have. I need lines to demarcate the outer region of the matrix, of the maze. I need lines for every time there's a wall, whether it's a south wall or an east wall. So let's demonstrate this with some very simple ideas. I'm going to create a maze. Let's make sure I'm running the exact one. I'm going to create a maze which is 100 by 100, and each square is 10 pixels wide. So when I view that, I get a maze that looks like this. It's very nice, it's very fast, and you see here this is the starting point, and this is the ending point, and if I traverse through my eyes, I can quickly see that this is the solution. Very nice. Let's try something more challenging. Let's make it a little bit bigger. Let's still do it like this. All right, now we're getting up to first grade mazes, and I might have to spend some time to wander my way through here. And the thing that's really indicative of this kind of approach for growing a maze is that you can see the depth first traversal that they actually took, and my goodness, this is going to be a long time to get to the very end. Let me try a really big maze. Let's do 800 by 800, and we'll only make it 5 pixels each. Oh my goodness. I've run into the problem with Python. So this is the problem with a recursive algorithm. At some point, you're going to run out of what's called heap space, which is the need to keep calling a function and calling another function. Eventually, when this comes back, it will say a simple note, the depth exceeded while calling a Python object. So it doesn't matter what language you use. It doesn't matter that this is Python. At some point in your language, you will hit this recursive depth stack. And there's nothing you can do, but there is. You can change that depth first search and make it non-recursive. This is a fundamental theme in many algorithms. You develop it using a recursive approach, and if you ever encounter any performance issues, you find a way to turn it into a non-recursive approach. The way that I'm doing it is simulating a recursive call. The way I'll do that is as follows. I'm going to create a path which starts my initial square. As long as I've got something in the path, I'm going to go ahead create my random choice, and then insert it right at the beginning of the path. That will keep growing the path that I'm working on. And whenever I reach a dead end, I mark it as black, and then I delete that from my path. So this path list can grow as large as it wants. And I know it seems interesting. Why do they put a limit on a recursive call? Partly it's a practical point of view. It usually means that you've run into an infinite recursion and it's a defect in the code. And I can have an array in Python grow 100,000 elements. Doesn't matter how big it grows. So my one small change is to take that recursive algorithm and make it non-recursive. And by doing so, I'm now able to tackle larger graphs and thereby construct larger mazes that are more interesting and challenging to solve. So I'll do this one, 800, 800, we'll do 10. Now, I wouldn't want to do this on my lunch break, but you can clearly see that it solved its purpose. It's a rather complicated maze. I can't even show you the whole thing here. It looks like a real maze. It's something that, to an untrained eye, I won't know where the solution is. And if I start my search, before I know it, I'm lost in the middle of a long traversal. So this maze algorithm, first of all, it's fun, but also it demonstrates one of the fine points about any recursive algorithm, that you may find yourself under certain circumstances that the recursion will fail strictly because of the performance on the computer you're running, not because of the algorithm itself. And in those cases, you usually can find a way to convert it to a non-recursive approach and thereby allow that same algorithm to proceed and work its wonders. So this is concluding the application for generating mazes using depth-first search.